Okay. So we're going to continue on with what Riemann did, and that is approximate the area under a curve by breaking it into a bunch of rectangles. And we've already had 3 different ways to attack that: left hand, right hand, midpoint. But we also have had some suggestions of other ways to do it. May mentioned the other day, one of our previous lessons, well, why couldn't we use a trapezoid? And the trapezoid is actually a more accurate answer. We're going to wait to get to that later. Okay, so 99% of this lesson today is based on Riemann asking one simple question. Okay? And when we're done, we're going to have something called a definite integral. We're going to have a method to get as accurate of an answer as possible. All those Riemann sums you did on day 42 homework are all approximations, and you see any directions. Use a Riemann sum with left-hand rectangles to approximate the area under the curve, or to approximate the antiderivative, blah, blah, blah. Today we're going to start working towards getting that value to be exactly correct. And we've hinted at this a little bit, and that's where this lesson today gets fairly conceptual, because I want you to try to understand what exactly we're doing. All right, so objectives. We're going to do some geometry today. And depending on how good you are at geometry, this could be either very easy or a little bit more challenging. But I'm assuming that you can all find the area of a rectangle. Is that accurate? Can you do a triangle? Can you do a trapezoid? Can you do a circle? If you're feeling saucy, can you do a semicircle? Okay, then you'll be fine. Okay. But there is some conceptual stuff at the beginning of this. So here we go. We got that picture. Now, that picture looks very similar to what we've done already, except for one big thing. What's the big difference, other than the cool colors? Andy? Beautiful. Okay. That's it. That's what we're going to talk about. Why do the rectangles have to be the same width? Everything we've done up until this point involves delta x being a constant. But now we're changing these things. Okay, so remember, let's back up to the last lesson. I had that cool picture going, and I kept making the number of rectangles bigger and smaller. And we agreed that if the number of rectangles was very big, then we would have as accurate an answer as possible. And then we said, in order to get it to the right answer, we want an infinite number of rectangles. Or we want the rectangles to be very skinny. Those are the exact same thing. Okay? Infinite number of rectangles, or rectangles with a width of 0. You with me so far? Okay, good. So in other words, we're going to do a limit. But we're not actually going to do limits like we've done already. We're going to do limits conceptually. Okay, so you'll remember that picture that I had where I slid the little bar to the side and the number of rectangles increased, or they got skinnier and skinnier and skinnier. Suppose I did it to this picture. I start shrinking the width of each of those rectangles at the same rate. All of them would go to 0, but they go to 0 in a different order. Which one would disappear first? We're all in agreement. Perfect. Which one would disappear next? Blue. Then next? And then the last one? Beautiful. Okay. You're doing great. In other words, green is the fattest rectangle in that picture. If they all shrink to 0, the last one left is the biggest one. Does that make sense? Okay. So what we're going to do is we're then going to say, all right, let's make some rectangles as big as I need them to be as accurate as possible. That is not an accurate picture. It's horrible. There's a whole bunch of overestimate there. But it illustrates what I'm trying to illustrate here with these big rectangles being all different sizes. Okay, so we go back to this funky sigma notation. And this is saying I'm going to take all of these rectangles. Remember, f of c I times delta x is the area of one of the rectangles. Okay, f of c is the height, delta x is the width. And I'm going to add all of those up. The sigma notation means add them all up, starting at 1 and going to n. Okay, good. So we know that already. Delta x is the width of one of the rectangles. In the last couple days, we've done it where delta x is consistent for all the rectangles. This one, they're not. We know that already, talked about that, we got that, okay, we said that already, we use the Riemann sum. Okay, so I basically just clicked through what I already talked about. All right, so this is what we're going to do, and this is what Riemann did. Riemann said, I'm going to find that fattest rectangle. And that's called the norm of the partition. He used the word partition to mean his rectangles or his deltas. I'm going to find the fattest partition, the norm of the partition, and I'm going to shrink that puppy down to 0. By the time I get that down to 0, all the others would be down to 0. Now, is there anything on this slide that you need to remember? Virtually no. So why am I doing it? Because I want you to appreciate how we're getting to what we're getting to. Shrinking the fattest rectangle down to 0 will guarantee that every other rectangle in that picture has also gone to 0. And that sounds a lot like a limit. And in fact, it is. And so you'll notice that bottom line of this slide, it says the area under the curve. That's an exact answer. Everything we've done up to this point has been an approximate answer. Increase the number of rectangles, shrink the size of the rectangles. We're still getting overestimates and underestimates. This bad boy gives us the exact area under the curve. And I don't want to say never. We will seldomly, if ever, do a problem that actually implements this, because I have a whole bunch of other tricks for you to get the answer to the problem. But this is where it comes from. And so in order to practice this, what we're going to do is we're going to take our functions and we're going to cheat. We're going to make nice, pretty functions that have all kinds of cool geometric shapes. And then practice that, and then we're going to get into some more challenging calculus later. But for now, we're just going to look at that kind of thing. That there's nothing exciting here, except you'll notice this bad boy over here. Okay. Up until today, our squiggly symbol never had numbers above and below it. It was just an antiderivative. So remember, when you take an antiderivative of a function, you get another function that we called an indefinite integral. You might want to jot that down in your notes, by the way. The indefinite integral takes a function and generates another function. This is a definite integral. A definite integral takes the antiderivative of a function and generates a number. That number is the area under the curve. Okay, did you get all that? Do you need me to repeat anything?
Can you say the definite integral?
Definite integral takes the antiderivative of a function and generates a number, and that number represents the area under the curve. These new letters that appeared here, A and B, are called limits of integration. And they're simply the starting point and the ending point. You've seen that before. Remember when we calculated delta x a couple of days ago? Delta x was b minus a divided by n, the number of rectangles. So what this fancy thing is saying, what this is saying is calculate the area under the curve f of x from A to B. That's it. This, on the right, is all the fancy schmancy stuff that Riemann wanted to use to confuse the hell out of you. Okay. So we're just about done with the concept, but I want to make sure you're with me. Are there any questions about that or anything you need clarified? Do you understand what we're doing here? Okay. Not how we're doing it, that comes later. Just what we're doing, not how. We're good? Okay, the big thing to remember is take the fat rectangle, make it down, go down to 0, all the other ones have gone there, and then we have our exact answer. Okay, so some of the things we did with derivatives also apply to integrals. If I want to take the integral of a sum or a difference, it's the difference of the integral. So the integral of the sum is the sum of the integrals. The integral of the difference is the difference of the integrals. Just like derivatives, you can put the constant out in front. You do this already, you just didn't even know about it. Just like when you take the derivative. when you take the derivative of 3x squared right now, you don't know what's the derivative of 3x squared? Derivative, not antiderivative.
That's 6x.
6x, beautiful. Did you do that by putting the 3 out here, take the derivative of x squared to get 2x, and then multiply it by 3? Or did you bring the 2 down and multiply it by 3 to get 6?
I brought the 2 down.
Right, so we've learned a shortcut to do that. The same thing is true here. You're not really going to put the c out in front, but it is a property that applies there. Why is that last thing true? This is a big one, by the way. Gesundheit.
Because it's still like this one, so
Talk loud, talk proud.
it's-
Say it again.
So the distance is like equal to 0 ultimately because there's like the rectangle is
What's delta x?
the area of the rectangle.
What's delta x in that problem? How wide is the rectangle?
0.
Perfect. Okay. That bottom thing, I'm actually asking you to find the area of a line segment, which is 0. It's a rectangle with no width. Okay. Does that make sense? Yes, Lynn?
So on
It's
the,
not a good way to start a question to start over.
on the first one,
Yes?
oh, sorry. It says, so it's B and then on the top and then A on the bottom for some of them, but this is the other way around for other ones. And I don't really know what that means.
No, A is always on, well, I shouldn't say always. Most of the time A is on the bottom.
Yeah.
We'll talk about in a second when it's not on the bottom.
Yeah.
Okay. In other words, A is always the number to the left,
Mm-hmm.
and so when you go from the left to the right.
I
What
think
if
I
it's
just-
upside down?
I think I just might have. Oh yeah, I just saw that.
So wait, what was the last property?
I'm sorry?
What was the last property with the 0?
That guy?
Oh,
That's what Via just explained.
yeah, yeah.
Okay. Then this is so obvious that it's almost hard to explain. If I want to find the area under the curve from A to B and C is in there in between, I can just calculate the area from A to C, calculate the area from C to B, and then add them up, right? If I want to know how far it is from my house, from school to my house, but I stop at the gas station on the way home, I could just calculate the distance from school to the gas station, from the gas station to my house, add them up, I get the same value. All right, this is the one you may have been referring to, Liam?
Yeah, that's it.
Okay. Notice, as he pointed out, my letters, my limits of integration are upside down. I'm supposed to go from the left to the right, but this is asking me to go from the right to the left. All you have to remember is that switch them, but you got to remember to put a minus sign out in front. Now, why that happens, I'll explain more in depth later when we in this slideshow, because something needs to happen in order for that to make sense. For now, you just need to remember if you want to switch the limits of integration, you have to include a minus sign.
Because then it's those two things are equal. So it's kind of like in physics where it's almost like you think about it going back in time, and it's like
Did
yeah.
you just use the P word in my class?
I'm so sorry.
Okay.
I brought this demon in here.
Yes, I'll let that slide this one time. See it? Okay. You know what? Don't do this. Just watch for a second, because this is really kind of silly. There you go. Put that pen down with some authority. Nicely done. Okay. All this is demonstrating is, I did this same example when we did derivatives, and it was kind of a waste of time, but from a mathematical pure standpoint, it's kind of important that you see this. So in order to find the antiderivative of that function, using the properties, I would split that up into a couple different things. Okay, so I would turn that into 3 different antiderivatives. I would move the 10 out in front, I would move the 4 out in front, I would move the 3 out in front, take the antiderivative of each of those, and plug and chug. Okay, so it's not a big deal. You're never going to do that, because it's just like the example I asked Leona how to find, I forgot what I asked, 3x squared. How to find the derivative of 3x squared. We don't apply all those stupid properties, we just do it, because we practice it enough that we know how to do it. the same thing is true here. You're never going to split the antiderivative of 10 plus 4x minus 3x squared into 3 parts and do each of those. You're just going to do it to get an answer. Okay. Any problems? Maya, I got a question for you. What bothers you about that slide? Anything?
I don't know.
No? Dimitri?
Oh.
Oh, wait, hold on.
There's no C.
Ooh, great. I'll come back to that in a second. Dimitri, anything in there that bothers you?
Aside from what Maya mentioned,
Okay. I've neglected to mention this. Remember, the plus c comes about because you're taking the antiderivative of a function to get another function, and you generate a family of functions. With definite integrals, there's no plus c. Okay, that'll cause some problems for some of you, because you'll put plus c's where they don't belong, and you'll forget to put them where they do belong. Good point, Maya. Anybody bothered by that?
It's a negative area.
Correct. Okay. So what does that mean? That means I found the area under some curve and I got a negative area. Up until this point, I'm pretty sure that in none of your classes you ever had a figure that when you calculated the area, a negative answer was acceptable. Okay, so now it requires a mind shift from what you've done for 17 or 18 years into this oddity that is all of a sudden that's a valid answer. What were you going to say, May?
No, it's nothing.
Okay. Well, where does that negative number come from? All right, so bust out your you already got your iPads there. Open either your calculator. I would use Desmos, actually, and graph the function 10 plus 4x minus 3x cubed. Question?
I know I'm kind of not so experienced, so, but like if that were like the like velocity, then like I don't know, something about like the area of a graph is like can be like the
Well,
velocity. Of
if you wanna bring the dreaded p word
Yeah.
into this, yes. If you're doing an acceleration to a velocity and the velocity is negative, that just means you're going the other direction.
Yeah,
There's no physics here. It's just a function. Okay, so graph the function. And what's the matter? Oh, that's your limit of integration. Where to start and where to end. Okay. Yep.
It's substituted.
If they ask for the derivative of that, do you think that's a rectangle versus the other, versus this?
Yep. Okay, so I assume you're all looking at the graph. What do you notice on that graph from 2 to 4? You might want to, for those of you that are on Desmos, you might want to open up the, what's the opposite of pinch? What is this action called? Does that have a name? Expand. You might want to expand your graph horizontally so that you get a nice picture of what happens between 2 and 4. Nathan?
It's all negative.
Beautiful. What do you mean it's all negative?
It's all in the fourth quadrant.
Beautiful. Okay. What you notice with this is that this graph, this region, is below the x-axis. There's negative values there. So this introduces a concept that will bother some people. We now all of a sudden have a negative area. And how are we defining a negative area? We're defining a negative area as any area that ends up below the x-axis. So when we did all those Riemann sums last week, and you've done all these other calculations of areas, I conveniently rigged the system so that all of the answers were above the x-axis. All of the functions were above the x-axis. This introduces the concept that if part of that graph or part of that area goes below the x-axis, that we all of a sudden get an area that generates a negative answer. Okay? All right, I don't want to beat a dead horse. I just wanted you to make sure you understand where that negative area comes from. And like Babe said, yes, that is an area under a curve, but it's an area that ends up below the x-axis. What's the matter? Oh, sorry, I thought you were talking to me. Okay, So I took this line here, which is 2x, and I used a Riemann sum. And this gives you another idea of the area under the curve. So if I was doing this function, and I asked you to find the definite integral from this starting point, that was weird, from this starting point of -2 to 1, what can you tell me about the answer? Liam,
It will be negative,
tell me why.
because it's more under the graph than above it.
Excellent. The area under the curve is bigger than the area above the curve. And hopefully that's a pretty simple concept. Now, we're not going to calculate that because I don't really care right now. I just want you to be able to put together the puzzle pieces that you're going to be adding negative area and positive area, and your answer is going to be one of three things. It's going to be positive, it's going to be negative, or it could be 0, depending on the function that you're using. Okay. I know you know this, but just as a quick review, you may have had a crappy geometry teacher. Area of a triangle is 1/2 base times height. Area of a circle is pi r squared. Area of a trapezoid is 1/2 h times the quantity b1 plus b2. You all knew that, right? And by the way, that's something they're not going to give you on the AP test. Okay, so let's start with this guy. I would like to know the area under the curve of the function 4 from 1 to 3. Go ahead. I'll wait. Oh.
No, it's just for
From 1 to 3? Make sure you just capture this. You have to capture this.
X equals 4. And your area of that 4 times
Do
2.
we have an answer? 8. Oh, I thought you said 8. Like, yeah, I'm right here. I'm so excited. Okay, good. Answer? Answer? 8. Maggie, answer? No. Yeah, that's good. Answer? No? Okay, Allie, explain it to us.
Like, y equals 4, so the line is not 4, you have to find the.
What kind of line? Be specific.
Horizontal,
Good. Keep going. I'm listening.
and then it's like, you have to just find, like, multiply the integral, like, on what it's in, like, 1 to 3, it's like 2 times 4.
Keep going. I'm listening.
I just did like 2 boxes inside, and then did like 2. 1 times 4 plus
I was
4.
feeling all fancies in my pantsies. I did 1 box. Okay. Doesn't matter.
So it's 2 times 4.
How far is this?
2.
2. How tall is this?
4.
4. What shape is that? Rectangle. Area of a rectangle, base times height. 4 times 2, 8. Done. Okay. That's where I was talking about using geometry.
Do you like always draw a graph? Like is that like some? Is there like a faster way to do it? Or-
Yes, but we haven't learned that yet.
okay, so like on AP test
There's-
you don't have to draw.
No. We're just looking at geometric shapes now to give you an idea, to put the puzzle piece, to start to put the puzzle pieces together. There's a mathematical way to do
Yeah.
that. We're just not
Just
ready.
later.
Yep, later. Okay. So, number 2, find the area under the curve. Go ahead. Why would I lie? Have I ever lied to you? I would want to. Why would I start now? What's base one? What's base two?
Wait, so
All right, we good?
Yeah.
10.5. We don't know what's better. Well, let's draw a picture, shall we? What's the graph of x plus 2 look like? It's a line, good. Hi, welcome to Algebra 1. Y-intercept of? 2, slope of?
1.
So where is that point? Okay, this is at 2. Where's that point located at? 5, right, because 3 plus 2 is 5. So this point is at 3, 5. This is what kind of shape? It is a trapezoid. What is the height of that trapezoid? 3, right. You got to look at it this way. So the height of that trapezoid is 3. What's base 1? 2. What's base 2? 5. Plug und chug. 5 plus 2 is 7. Times tree, 21. Divided by 2. 4 times a half. If you're feeling saucy. Okay. Problem so far. Numero trace. Oh yeah. That just happened.
This is one of the It's not.
divide by 2, bro.
Come on, girl.
How do we find the
You didn't have that when I walked over there.
It is not a semi. It is
Okay, so what shape is that function? Yeah. What does that mean, Lauren? Use your words. It's a semicircle, correct. With a radius of, Amanda?
2.
Beautiful. 2. Negative, whoops, negative, what? Hey, where's this point, by the way? 2. Okay. The area we're looking for is that. Okay. So, that's a semicircle with a radius of 2. So 2 squared is 4. 4 pi divided by 2 is 2 pi. Yes. Good. Good. What if I did this?
Just do a quarter.
That'd be
Do a quarter of a circle. What if I did this? Zero. I can't fool you guys. That's right. Well done. Okay. The basic idea here is that we're finding the area of a function between the function and the x-axis. If the x-axis ends up on top or the function ends up below the circle, then you do the exact same thing, but you have negative area. So there's our rectangle, there's our trapezoid, there's our semicircle. Just to review, for those of you that have forgotten, this function, in the general form, the square root of r squared minus x squared plus or minus, that will tell you your semicircle. If it's positive, it's the top part of a circle with a radius of r. If it's negative, it's the bottom circle. Why don't we ever use the left and right part of the circle? Liam? It's not a function, correct. This is not a function, therefore we want nothing to do with it. Last one. How will you find the area under the curve of the absolute value of x going from -3 to dos? That's Spanish for 2.
Thank you.
You're welcome. I know some of you are taking French or Italian.
Cantonese. It's 5.
It's 6 points.
Can I share a safety tip with all of you? Anybody a coffee drinker?
No. Yeah.
No? So I just started doing a pour over coffee. Do you know what that is? It's amazing. The coffee is so much better than those stupid Keurig things. But I learned this morning the hard way not to chug the end of your cup of coffee because that's where all the grounds are.
Oh, wait,
So I've been picking coffee grounds out of my teeth all day.
how do you, what's it called?
Pour over is a little container that you put the grounds in with a filter and then you pour the hot water and it runs right. It's like
Oh,
but it's cleaner, it makes a great cup of coffee. But some of those little coffee grounds get through, and so you get like this little mucky muck at the bottom. And I didn't realize that this morning. I just kind of slammed the rest of my cup of coffee, and then I was like, oh.
Let's get another filter and filter it again.
Double filter?
Or get like a more heavy duty.
Not a bad idea.
It's
not a good way to start a question.
This is a kind of general like math question.
Yes.
So when you have something like this,
Yes.
this is power of 2.
Yes.
Is it just convention to like by default have it above?
No, it's above because this is a overall it's a positive.
Yeah, but when you just graph it, that's not right. If you just graph it, is it? You could technically do that, but is it just convention to do it that way?
You can't do that because if you plug any number into that equation, it's going to
In this class?
yeah, because, well, when you take the square root, you take the positive or negative. Because there's no minus, the assumptions that that is a
Yeah.
positive
So
value.
okay. And then
Hold on, I'll be back.
You did it in the wrong way. No, you did it wrong. It's going to do it.
Alright, go ahead.
this is a question on the homework.
No, not homework now. Finish lesson. Anybody? Answer?
6.5.
6.5 has been the presented answer. Any counterpoints? Any agreements? Why?
Because the area is all in the positive direction and the absolute value goes like this, so you find the value of this side, that side, and
What?
that side.
Okay. Yes. What are the shapes of those sides?
triangles.
They're triangles. Good. So if you graph it, it looks like that. You all know that the absolute value function is that V-looking thing. We've talked about why it's a V-looking thing. Maya and Anthony, you weren't here for that, but do you know why the absolute value looks like a V? Okay, we're gonna take a 30-second sidebar and explain it to you because it is important. Anytime you take the absolute value of a function, it takes whatever's on the bottom and flips it over. Okay, so for instance, if you had this function, and you were asked to graph that, you would graph x squared minus 4. It would look something like this. And then you take anything below the x-axis and flip it over. So this would be your final answer. You with me? The reason the absolute value of x looks like a v is because it takes the graph of y equals x, which is just that 45-degree line, and flips this negative part up like that, and that's where your absolute value. Okay, I'm not trying to burden you with stupid math trivia. This, I mentioned, is because this will help you with these guys when they pop up. Okay, good, sidebar. So, as May said, once you graph that, whether you graph it, sketch it, picture it in your brain, whatever you do, you end up getting this picture with two different triangles. One is pink, one is brown. Find the area of each of those triangles. Life is good. How do I find, May, I'll ask you, how'd you find the location of that point right there?
Okay, I like knew it was up to 2. And it's like, that's a right triangle.
Can you simplify that a little bit more?
I mean, like, I just found like my 2, because it's like
Plug and chug.
1.
That's what I thought you said.
Yeah.
Plug and chug.
Yeah, plug and
Right.
chug.
Yeah. What's the absolute value of 2? 2. What's the absolute value of negative 3? 3.
Yeah.
Okay, good. We good? Questions? Oh, 6.5. Lauren, question? Oh, I thought you had your hand in the air like you just don't care.
No, just doing math moves on the next one.
Oh, that one. Oh, yeah. The math moves there. In case you want to practice that or want to perform that in the next talent show. That would be great. Yes. You do like a game where you come out and you dance and then the audience has to guess your function.
This is like a
Name that function.
No, this is like a YMCA dance where you're just like, whoa.
Yeah.
Like a true